Hello. I was wondering how this mission complements Dragonfly. What can it do that it can't? Is it going to go after it? Is it going to be part of it? What's up?
Yeah, so the fundamental thing here is that Dragonfly got selected by being the lowest possible risk you could really come up with for a Titan mission. The relocatable aspect of Dragonfly actually allowed them to reduce risk, because if they get a crappy landing site, they can just move. And they also, as part of this risk reduction philosophy, they chose to go to dry areas of Titan in a dry part of the year. And so we're doing like the opposite of what they're targeting and going for the liquid, for the rainstorms, for the lakes. So they're going nowhere near the lakes. And that's really the answer that we do complement Dragonfly. It's basically we're like 1 minus Dragonfly. And we'd be a decade or two later probably too. So.
Hey Quinn, amazing work, may I add. I recall you at first really focusing on the capillary action. Looks like you've taken a closer look at the flight body and then the vehicle itself. So I'm glad to see that. And this may not be like a really fair question. Can you talk about what is similar and what is different about the environment on Titan compared to Earth? I mean, you look at it and, you know, as an analog, it's very similar, right? But chemically, it's completely different. And so, you know, using bioinspiration, I think, is really, really useful because of that. And can you just talk a little bit more about that?
Yeah, so they're very similar. The biggest difference is it's like 25 to 35 times easier to fly on Titan.
Okay.
It depends sort of what your metric is. There's often people use an analogy, if you had like wings attached to your arms, you could fly. And so it's a nitrogen atmosphere, similar to ours in that respect, right? It's just denser. It's 1.4 times denser. I think that's right. 1.4. There's also a 4 in there somewhere. But the biggest difference as far as aerodynamics goes that I've noticed is the viscosity is much lower. So nitrogen at cryogenic temperatures like 90 Kelvin has a much lower viscosity. And so when you're talking about an analog, that's the biggest difference that I've seen. I'm still trying to understand how this situation with that gives us a higher Reynolds number, yet we're nowhere near the speed of sound. And so we're in this sort of weird region you don't get in flight on Earth. Other than that, the methane does take the place of water in the hydrological cycle, so it's very similar, but there's weird things that happen, like the clouds are much higher. They're 30 kilometers high to make the rain, and a lot of times the raindrops don't even make it to the surface. And so stuff like that, it's hard for us to understand. These larger methane raindrops, maybe 6 to 8 millimeters, that can evaporate on their way down and not even touch the surface. So a lot of that liquid in the lakes probably landed at higher elevations and ran down through rivers to get there.
Okay.
It's pretty interesting.
Awesome. Thank you.
Larry Forsley, NASA Glenn Research Center. This is a marvelous device you've got here. I'm assuming that when you calculated Reynolds numbers, taking into account the pressure, also taking into account, though, the lower surface gravity, coming up with your planing speed. Is that true?
Yeah, there's 2 ways to calculate planing speed, and one of them has gravity factored out, and one of them has it in. I use the larger of the 2. So the number I had on there was 22, the other one would be 17. They're both much higher than our cruising speed of 11. And we could fly at closer to 7 meters a second with a higher angle of attack. And so we're way under that. The planing speed just simply doesn't look like something we'll be able to achieve unless we're like purposefully flying down into the liquid, which might be an interesting way to test that. Now the other thing is this planing speed, the whole idea of hull speed is a cheat code that the maritime engineers use. And scientists don't use it. And so I don't know what assumptions are baked into this, and I don't know if I could figure it out without going to marine engineering school, because you know, they just use it as a tool, and then scientists don't, and I don't know. It's tough to figure that out. So I could hire a maritime engineer as a consultant, I suppose, but just by checking it out, it looks like we could just fly out of it, and suction would be a bigger issue than planing.
Well, with regards to that, I think, what is it, the David Young Navy facility, where they do a lot of these measurements themselves, you probably can go through their literature and find the answer to that, at least how the maritime group has done the numbers.
So if it's empirical, it's kind of weird, though, and also, why doesn't density show up?
Yeah.
So I messaged a seaplane pilot. I haven't heard back from him, but if you take off on freshwater and saltwater, is the planing speed the same for your seaplane? Or is it close enough you don't even notice, you know?
Last question is, are you at the critical temperature for methane?
So this is an interesting thing, okay? The biggest problem with icing and methane is nitrogen depresses the freezing point and as the temperature of methane drops, it sucks in more nitrogen from the air. And so below 14 kilometers altitude, freezing of methane can't take place. And so the critical temperature would probably be about 14 kilometers. And Huygens, you could just go look up and that would be the temperature, I guess.
Edward Balaban, NASA Ames Research Center. Great talk, really enjoyed it. So I may have an idea for a vehicle for you, but it might be kind of slow. So I wonder if you have a range, an optimal range of airspeeds where you think sampling would be done best.
For like the shoreline situation?
Well, whatever. So your vehicle
Yeah.
is flying through the air. What is the optimal range of
So
airspeeds?
you can fly depending on, like this vehicle, we obviously have a power source and that sets the size and it's huge and that's a different story. So
Yeah.
if you can fly at 1 meter a second, you can fly at 10, you can fly at 20.
Right.
I do think if you plot the flight power curve after 20 or so, you start to lose efficiency for how far faster you go. So you can go from 10 to 20, you're still, the efficiency is sort of a 45-degree angle on the chart. So you can go to 20 and you're not going to waste more power than a 10. But so you're sort of 1 to 20 is a good range for meters a second for flight.
Yeah, that's as far as efficiency goes. I'm looking more for the sampling operation.
So that
Right.
shouldn't matter from velocity because of boundary layer effects. So as you go faster, because at the skin, we can effectively assume it's zero. And you do see that if you look out the window, even of a hurricane chasing plane, the liquid's just hanging out.
Okay.
And so the boundary layer effects should. Now with
should
the lower
negate.
viscosity, I think that would give you more favorable boundary layer conditions for that. It
Okay.
hurts my head to think about that. So.
Okay. All right, thank you.
Yep.
Perfect.
Thanks, Edward.
Hi, I'm Hadley Douglas from the University at Buffalo. I was wondering if this mission could be adapted to go to other planets and moons and what those planets would be.
Yeah, so Venus, I think actually with the Breeze flyer, it would work very well. I'll probably be using that as an example for why competing approaches, because I think that if you wanted to sample liquid on Venus using that flyer, competing approaches that would work on Titan may not work for Venus. And so, also Earth. So Venus and Earth are the only other two. They're both compelling cases though, but in the case of the Breeze flyer, that skin, if you have a section of it that was just woven differently out of your Kevlar, and assuming sulfuric acid, which is the rain on Venus, if it didn't eat your skin, you could just find a way to skim that sweat off the inside of the surface, and you still have that flexibility. So that's really cool. I thought about that when I was watching your guys' presentation, so.
Thank you.
Yeah.
Yeah, I'm wondering what analogs are available for you for testing apart from the mist in Washington State, because the methane mist is going to behave differently.
Yeah, so Earth is a good analog though, and we think that the NASA Earth Sciences program, we could do flights. So if we wanted to limit the gravity case, we would be stuck to the NASA flight grant, and we'd be having to, inside the airplane, supply our own atmosphere to do our analog testing. But if we did a NASA Earth Sciences flight, we could potentially have an instrument on the outside of an aircraft, and we would just know we're going to have a higher gravity. We're not going to be, maybe you could give the pilot $20 and he could give you a low gravity for, I don't know. But that's sort of the trade-off there, is we could have additional funding sources at a 1 gravity analog and then be limited, like everybody else doing capillary studies, and low gravity for the NASA flight program.
Hi, Leaf Sortie from RPI. I'm just curious, what would your power source be if you're going to fly around?
So I did the math for this using 3 MMRTGs, and that was like, in my mind, like what's the worst nuclear power source I could find? Now, if anyone doing magical nuclear power sources comes with a better one, you could send it to me, I'd be happy, that's great. Okay, I picked, what can we do? Now, it may not be feasible to get 3 of these because the DOE is only making so much plutonium a year. I did the best I could to pick a realistic power source. So 2 of the RTGs are for airplane flight and charging batteries the same way Dragonfly does, the trickle charging method. And the third one is for general operations. And this allows us to charge, we can do a flight every day or 2 with a 10,000 kilogram aircraft that would have to be launched on Starship. And then we could do 30-kilometer altitude flights once a month, the same sort of math.
And I guess I'm just curious, why not be a balloon?
I think that we could use this system for balloons or any other, even possibly a Dragonfly clone. So this system is really an aircraft-borne system, whatever the aircraft is. I chose a flying boat. I think the relocatable lander aspect of it and not relying on perpetual flight is an advantage and puts you in sort of a unique frame of mind. So, yeah. All right, thanks everybody. I'm 22 seconds over.